brittle materials.
Would they be too difficult to break if you had a sheet like that?
Your sheet of nanocrystals is not
Very
difficult to
easy to
break.
break.
Not difficult to break?
Yeah. A very thick sheet.
Very easy to break.
Snap it, because just by itself, it's kind of brittle.
Okay.
But the idea with everything everyone's done with that is either A, they're playing with the charges on the coatings, or it's acting as a reinforcement for another material, whether it's paint or epoxy.
If you put like
plastic.
enough of it together, would it be stronger then?
No.
No,
it's the same thing.
well, it's stronger, but it's still
But still brittle.
it's
like
just
a
a bigger
ball of
piece
it.
that's heavier, but it's still very
So
brittle.
break pretty easily?
But I guess if you made a huge block of it, yeah, it'd be strong like a brick, but then you're
With
using a ton of it.
So with like a flexible display technology, you probably use the more plastic or the more saran wrap type.
Yeah, but like I said,
Obviously you
unless
would
of
want it
course,
to break.
unless you're using it more as a reinforcement, in which case the brittleness doesn't. The brittleness of all the nanocrystals together is no longer the case because they're all separate and essentially reinforcing the plastic and resin around it. And so
It's kind of like
it's going to behave very differently.
So which one were you using for like bulletproof glass?
The ones they focused on the most are the nanocrystals so far. So what they're doing is they're essentially extruding it in a very micro filament. So it's actually a filament that's, like a human hair thinner.
Right.
And then when they do that, they're actually taking what are these little stiff rods and are actually getting aligned along the length of the fiber. And then they take this basic, twist the fiber, and they just kind of heat melt the whole thing into a sheet.
Mhm.
And that's kind of how they've been processing it to this point.
I think we were talking about that when JY first presented to us, how it was difficult to get them all lined up like that.
Yeah.
You have to use like magnets or something like that.
You can use that, and I know people looked at it. I don't believe the Army is, though. I think the Army is essentially using, they are doing electrospinning, so I guess there might be a charge at the spinneret. I don't know enough about
I
it.
know some people use electric field or magnetic field to line up the nanocellulose to make it stronger.
Yeah, so I guess they are doing essentially what they call electrospinning, but I don't know if you enough of the detail to tell you exactly how that's happening. I know what they're doing is they're making a very thin fiber with aligned nanocrystals in it, and then kind of heat, thermally melting all those little fibers together into a sheet.
So then is that pure nanocrystals? Or
No, it's a reinforcement for the
it's definitely, I was going to say, because it's brittle, that's not bulletproof, obviously.
Yeah. And that's where I said before that they would prefer to use polymethyl methacrylate for making these spinneret stuff. But the melting point of that is just a little bit higher, and things start to degrade with the cellulose. And so the question is, are there things we can do to kind of stabilize the cellulose to a little bit higher temperature, or working with a different plastic rather than?
And that's where they come back to you to further the research, or?
Well, right now I'm mostly focused on production.
Okay. Sure.
And if people come up with how to process things a little bit differently, I can work in that in. And at this point, I have no time for that. I'm just trying to figure out how to optimize production.
Okay. That makes sense.
I think I got all the bugs worked out with nanocrystals. The nanofibrils, I still have a few things to figure out.
So you've got an end result, like the nanocrystals that you are making. You're not changing that so much as you're just trying to change how you make it.
Yeah, just
trying to make it as efficiently as possible.
Yeah. And there are things, right now, there's a plant that went up in Canada by FP Innovations, which is actually larger and more of an industrial-based approach. Mine is kind of in between. There are things that I'm doing that there's no way you would do in industry, but I did it because of convenience and lack of money.
Right.
They got like 35 million. I got 1.5, and they got 35 people. I got 1.
Nice.
So, but for example, the sulfuric acid, they're working on ways to kind of regenerate that. They're working on ways to separate the sugars from the hydrolysis from the acid, and then use that for biofuels. Whereas I'm just neutralizing it and dumping the whole thing down the drain, which is in the long run impractical, but on the scale for R&D material is okay.
Yeah. You had mentioned working with the University of Maine on some flexible products or something?
Maine
No,
is working
Maine
on
is
the third kind of nanomaterial.
so this kind of different kind of, as I said, what Lucas is doing here, the SF is not in the patent.
Right.
The patent is using fibrillate, which is through mechanical fibrillation. And for doing so, we actually using enzyme to take out some amorphous cellulose and make fibrillation energy cost less. Okay, so Maine
Go back and just define what Maine is doing. Then
Maine doing just the fibers goes through mechanical milling. That's all they do. Okay, they could integrate this patent into the main facility. Okay, But the issues, of course, a lot of issues to resolve. Where we're going to find the application of this particular nanocellulose. That's the thing. And then you also have to get the sugar recovery process too.
The third nanomaterial that Maine is focusing on, like you said, is a pure mechanical refining. You just refine and refine and refine under the right conditions, the heck out of this. And what you kind of end up with is kind of what I would call microparticle, which is kind of that has lots of little nanofibrils coming off of it. So it's just a very extremely fuzzy particle.
It's not complete separation. It's very hard to do complete separation using mechanical method.
When you start with pure cellulose, it takes a huge amount of energy, a huge amount to even get to that point. But you can play with the balancing. You can do some hydrolysis, either enzymatic
Even
or
acid.
acid.
Yeah,
And that makes less energy, but inherently a weaker material, so it's balancing how much you pre-treat it with how much energy it takes with the strength of your final product.
the happy point.
Find a happy point. There may be different happy points for different things.
We have a small scale up here.
So that's what Maine is working on.
Is there a certain material that you're trying to get to that will be like the mass production product, or is there going to always be like different types of it that are going to be?
That's the whole problem right now. We haven't figured out what they want, or
right
people
problem?
haven't figured out how to
is there
use this
something that
material.
everybody can use, kind of a thing? That's I guess what we're trying to get to.
Yeah.
Because I mean, they're all kind of using the same stuff, just in different forms. It seems like. I mean, if you were to use the panel of a car, or for flexible display, or for biofuel, I guess.
It will be different for sure, but we haven't figured out what exactly want.
And that's really why this plan was built, to let someone figure that out.
What is the source, I guess, that you're? I mean, obviously, like trees, and you break all that down into the fibers, right? And you're turning the fibers into whatever you want to, essentially, right?
But there's like, what he's trying to say is there's no like market that you're like,
No
you're
market.
trying to specifically like.
There's no
target.
market right now.
Well, you have a material, yeah, and it can go into a lot of different markets for a lot of different reasons. Properties, like I said, or like we were talking about, it's conductive, so it can have.
It's not conductive.
It's not conductive.
No, the cellulose is not conductive.
I thought.
Well, yeah, but the two materials I'm making here add the sulfate charge and add a carboxylate. That makes them conductive. The stuff Maine is doing, they're not adding any charge functionality to it, so it's really no more conductive than cellulose.
I guess I shouldn't be using scientific terms when I describe it. I'm talking like, so it has the ability to have like electricity go. It has
Either
you can have a
it
screen
could be
on
a base layer for something conductive,
Okay.
or like I said, the two materials I'm making here, I'm actually changing stuff, and it is more conductive than the original cellulose. And whether
What's
it's conductive
a
enough,
flexible display then that has flexibility and it has the ability to like have a screen on there?
I think either they're using the charges on the material to kind of plug in ions in a certain way, just like they do on a thing, or they're doing an extremely thin coat of silicon and metal. To make a microchip, you basically take silicon and then you embed it with lots of different ions, different patterns, and you make transistors and all that stuff.
So that's what they were trying to do with like the e-paper that you were talking about.
Yeah. You're talking, 10 nanometer thin coatings of electronics. They're very flexible. As long as the base material is strong enough to kind of hold everything together, and get figured out. And how flexible does it need to be? Does it need to roll it tight, or is it just kind of like a negative?
Fold it up and
neutral? Who knows? I don't know.
You're definitely not talking about a pure nanocellulose like sheet that, say, if you had a frame around it with all the electronics on it, it wouldn't be able to send it through.
No, it can. I mean, they're making something like that. Yeah.
Like I said, the cellulose I'm making has a certain conductivity, not as high as like a wire,
Right.
but higher than the pure base cellulose in a tree or that nanocellulose Maine is making. And if it's enough conductivity or not enough, and I can change to a certain extent, like the nanofibrils, I have a certain amount of control over how much charge I put on it, up to there's an upper limit.
Mm-hmm.
If that upper limit is too low, then we have a problem. But if upper limit is high enough, you can control kind of things in between. It has an effect on strength and how much energy you need to refine it, but it also affects properties like conductivity.
So that's definitely one of the big aspects of what we're trying to figure out is what kind of products can we do with the electronics, really. And that was what we kind of, in the initial presentation, what we were thinking that would be part of it. Otherwise, sugar-wise, then we're really just talking about reinforcement materials. Then we're talking about like automobiles or body armor or building supplies, packaging.
For the particular pattern you're going to do, probably there's no conductivity issue. You can't use that.
Okay.
If I were to make a guess, I think the 3D printing reinforcement is an obvious application. That as 3D printing moves up, this nanomaterial kind of as a reinforcement for that. Because there are nanoclays, there are nanosilicas that are kind of in the price range, and of course you get to carbon nanotubes, which are much more expensive. They could work to reinforce in that kind of thing, but they're much more expensive. But then the fact, the biodegradation, biodegradability of it, so if people build something and then they throw it away, they don't have to worry. Well, it depends on the rest of the resin, but there's recyclability, there's biodegradation, biodegradability.
Well, if it's not a pure nanocellulose, then the other things in it has to also be biodegradable, or else it wouldn't really make sense. But in its pure form, it is biodegradable, so you could throw it out essentially.
What about like the aerospace industry then? I know you were saying like with the heat and the cooling, with a certain heat temperature, that's probably a market that would be alongside.
Well, there would be the windows. They can make the bulletproof windows. They would probably be strong enough for windows in the airplane space and everything else. Still have the transparency, so they'd be lighter weight.
That won't have any like issues with temperature changes and stuff like that?
Sure, but the question is, are they solvable issues? Like NASA was just here yesterday. We were talking with NASA, and they want to move from metal-based booster rockets to something lighter weight.
Oh, really?
And one of the issues has to do with making it so that the fuel doesn't leak through coatings. And they were interested in can the nanocellulose be used as a coating inside these polymer-based, resin-based fuel, fuel boosters. Because one of the big questions was what's the permeability, and actually because it's so small, they pack so tightly, there's essentially almost no space between the cellulose for fluid to kind of permeate through. That's good, but then of course there's how do you get it to stick to the inside of the tank? There's expansion and contraction either through humidity or
How does it
thermally.
handle a booster rocket?
Because the fuel's super cold.
Well, they were just here yesterday, so we don't know any answer to any of those questions.
Not that fast.
Sometimes it puffs on.
They just want to come by and talk and see what we are. Can you send some samples and we'll start playing with it, which is what everybody's doing.
Yeah. With your patent and I'm kind of switching topics, with the biofuels and the sugars, how does that, you mentioned it's limited as to the extent maybe of the biofuels or
The applications?
the applications. Is there any, I don't know, where do you think that might go? Or
Well, the sugars, once you get the sugars, it depends, what kind of feedstock you use. You can get a very pure sugar. In that case, you have so many applications, goes through the chemical conversion. There are so people start with the sugar doing all kind of wonderful stuff. The problem, the sugar is expensive. In this case, actually, the sugar application is pretty broad.
And
Plastics
there's one
example,
more-
chemicals.
There's one more piece of that, and that when I hydrolyze cellulose with sulfuric acid, you make sugars. But one more thing you can do is in these strong acidic conditions, sugars actually decompose to something either if it's glucose or 6-carbon sugar decomposes something called hydroxymethylfurfural. It's a 5-carbon sugar like xylose that decomposes something called furfural. They're similar, but small differences. And these can be used as petrochemical feedstock. And you can essentially hydrocrack them and do almost anything with them once they get into a furfural. So there's a lot of interest in furfurols. And the sugars in these kind of acid environments will actually degrade to a furfural. The problem is in these environments, the furfural can actually degrade even further and they can start polymerizing into black goo tar that basically is a giant mess. And so the trick would be, with absolutely no use. So the trick would be you could take the acid and you could potentially convert it to a furfural or a hydroxymethylfurfural, and as long as you can stop it there, you have a very valuable product. But if it goes too far, it gums up all the equipment. And so there have been pilot plants that have been playing with that, but that's another direction to go other than sugar. Sugar is a valuable place to go, but there's actually other places you can go into other industries.
Yeah, for their study pattern is without involving acids, so that's not an issue.
guess the main point is there are many different directions they can go. There are directions for the sugars where they can go. There are directions for the products and all different places it can go. There aren't any specific answers.
For the sake of our limited time, we're trying to figure out maybe one thing that we can do kind of, more effectively, because